Hello everybody, welcome to Forces Unit 1, Lesson 5. This lesson is about mass and weight, how you calculate weight and work. For this lesson you will need something to write with, a pen or a pencil, something to write on, a piece of paper or a book, whatever you've been using. You can also use a calculator if you want to. If you don't have those things, pause the video and go and get them now. Okay, let's get started as we always do with a little mini test of questions from previous lessons. Pause the video, write your answers on a piece of paper, and when you press play, we'll go through the answers. Let's see how you got on then. What is a contact force? That is when things have to touch for the force to act. It's the touching bit that is important there. Examples would be friction, air resistance, and tension. What is a non-contact force? Well, that's the opposite to the contact force. No contact needs to be made between objects for the force to act. We're talking here things like gravitational force, electrostatic force, and magnetic force. Scalar quantities are things where you can measure them, put them into calculations, etc., with just magnitude. That is just size. If you remember back to last week, we were talking things like 4 kilograms in 17 seconds. There's no 4 kilograms north, south, east, no 7 seconds west, that kind of thing. It's just the magnitude or the size. Vector quantities, you have your magnitude or your size, and you also have to have a direction. How do you find the resultant force of two forces that are not forwards and backwards? Well, you remember this is the problems where we had the diagram, maybe one force going horizontal, one force going vertical, or going across at an angle, and the resultant force is somewhere sort of in the middle. Well, little method, we start off with some kind of scale drawing where the length of the arrows has to represent the size of the force. It doesn't have to be 5 centimeters, 5 newtons. You could have, say, 5 centimeters representing 10 meters, each centimeter representing 2 newtons, or 4 newtons, 10 newtons, 100 newtons. Whatever works, as long as they're both drawn to the same scale. You draw a second arrow at the end of the first, so perhaps you'll pick the horizontal one as your first arrow and then draw the vertical one starting at the end of the horizontal one. Where it ends up, you draw a diagonal from the start to the end, and the diagonal is the size and the direction. You'll need to measure it for the size, and the direction, well, it's simply the direction. You could, of course, draw a line going upwards and use a protractor to measure the angle, and you could actually represent it as a bearing if you wanted to. Well, you got those right. Well done. Let's look at a few new ideas today. So the first new idea to look at is mass. Mass is to do with the amount and type of particles something is made from. So if you've got a substance made of twice as many particles, you've got twice the mass. Likewise, if you've got something made of the same number of particles, but they are different type of particles, say oxygen compared to hydrogen or lead compared to copper, then it will have a different mass. So it is actually a combination of both of them, the amount and type of particles. It's the same everywhere. If I've got a mass of, say, 85 kilograms, I'm 85 kilograms whether I'm on Earth, in space, on the moon. It never changes. It's the same on every single planet. It is the same in space. Gravitational field strength. This is how big the pull of gravity is at a particular place. In space, gravitational field strength is essentially zero. There is a little bit of gravitational field strength because you, for example, you can be in space and the Earth has got some gravitational pull from the sun, but to all intents and purposes, it is very, very, very low. And as I say, it's different on different planets. On Earth, it is 9.8 newtons per kilogram. Weight is the amount of downwards force that you have. Now, I've highlighted force in red because weight is a force. Weight is measured in newtons because forces are measured in newtons. It does depend on your mass. So if you've got more mass, you have more weight. And it also depends on how big gravitational field strength is. Now, gravitational field strength is the same everywhere on Earth, more or less. It is technically Some places in the Earth it is slightly different, but very, 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 very small change. So your mass will give you the same weight pretty much everywhere you are on Earth. Weight, there's a little calculation here. Weight is mass times gravitational field strength. So simply multiply the two together. But I've done quite a bit of talking, so let's write down some key ideas. So these are the things we've talked about so far. Apologies, there's a few to write down, but it's important you get these ideas recorded. So if you want to write them in your book on your piece of paper now, pause the video and then we will continue. Let's have a go at a couple of problems then. How heavy means what is someone's weight? I've got the problem there for you. You can have a quick read through that. We'll dissect it in a moment. The way you start all of these problems is with the equation. So there's our equation. Weight is mass times gravitational field strength. So let's have a look at the problem, see what we've got. A man has a mass of 85 kilograms. 85 kilograms, then you can use a highlighter, you can draw around it in your pen, whatever, when you do these problems. 85 kilograms is his mass. Gravitational field strength is the other one, so I'm going to put that in. And weight here, well, weight is the unknown. So when we substitute in weight, well, we don't know what that is, so we're going to write out weight. Mass, substitute the number 85 in. Gravitational field strength, 9.8. So we put that in. Using your calculator, quite simple. Just put the numbers in. Comes out as 833. Almost finished. The last, most important step of this really is the unit. Weight is a force. Weight is measured in newtons. So that is how you do those problems. One for you to have a go at by yourself now, and I'll go through the answer at the end. So there's your problem. Read it through. Follow the same method as I did. I'll go through the answer in a moment. Pause the video. Okay, let's see what you should have done. Well, you should have started off by writing out the equation. The next stage is always to go through the problem. And on a GCSE exam paper, it's perfectly okay to draw circles around things to highlight what you know. You should have identified the mass as 55. Gravitational field strength, 9.8. And the weight is the unknown. So substitute those in. 55 for the mass, 9.8 for the gravitational field strength. Gives you a weight of 539. Obviously, last stage is always to make sure you've added that unit, and that is what you should have done. If you've got that right, well done. Let's have a go at some more problems then. Same sort of thing this time, except the gravitational field strength is going to change because we're on different planets. Have a go at these. Pause the video. Okay, let's see how you got on. Let's just move the table over and give ourselves a bit of space to do our workings out. So for the first one, for Mars, well, it's always mass times gravitational field strength. Substituting 85 times 3.7, she should have come up with 315 newtons. Very similar method then, write out the equation, substitute, calculate, and add the unit for the moon. And you should have got 136 newtons. For Neptune, 952, and for Venus, it is 765 newtons. You'll notice that the man has a mass of 85 kilograms, and he has a different, so that's the same everywhere, it has a different weight in different places in the universe. If you got those right, well done. Couple of did you know questions for you now. This is things that people often tell you about gravity. Gravity gets bigger when objects have a bigger mass. What do I mean by that? Well, the amount of gravitational field strength I've got is because I'm stood on a very, 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 very large mass called the Earth. If the Earth was heavier, if the Earth was a bigger planet, then the amount of gravitational field strength that I would have would be bigger because the mass of the Earth would be bigger. Gravity also gets bigger when objects are closer. So the distance I am from the centre of the Earth affects my gravitational field strength. In actual fact, if I went and stood on the top of a mountain, my gravitational field strength would actually be slightly lower. Not probably enough for you to measure, but technically speaking, you would lose weight by going to the top of the mountain. In actual fact, you'd lose weight because you have to walk there, but you know what I mean. Next key idea in this lesson is work. If you use a force to move an object, you do work. So if I pick something up and put it on a table, I've used some force, I've moved it a distance, I've done some work. If I drag something across the room with a piece of rope or push something across the room, I've done work. I've used a force, it's gone a certain distance. There's a formula to work this out. Work equals force times distance. Work is measured in joules, force obviously newtons, distance measured in meters. Let's move those things to the bottom of the page. And then if you want to add them to the other key ideas that you've all written down so far this lesson. Okay, pause the video, copy them down. Okay, let's move on then. Let's do some calculations. How much work is done when 100 newtons pushes an object at 7 meters? Little problem for us. Well, it's the same method as any of the other problems that we've done. You start off with the equation. This time it's work equals force times distance. You go through the problem and you highlight what you've got. So we've got work. I put a little question mark there this time to show it's an unknown. 100 newtons is our force. 7 meters is our distance. So once you've worked out what you've got, and as I said before, on an exam paper, you are perfectly entitled to go around and put circles, underline, or do whatever you need to do on the actual problem on the exam paper if that helps you. What you need to do now is substitute. So work, we don't know, so we write in the word work. Force is 100 newtons, distance 7 meters. Do your calculation, work equals 700. And don't forget at the end, you've got to add in your unit. The work is measured in joules, so we use a capital J for joules. Let's have a go at another calculation now, one for you to have a go at. Pause the video. Let's see how you've got on them. What should you have done? Start off with the equation. Then you need to go through the question, highlight what you've got and what you don't know. So work, you don't know. 400 newtons is your force, 3 meters is your distance. Substitute all of that in. We write out the word work because we don't know what the work is. Force 400, distance 3. Multiply them, 1200, add in the unit. Work is measured in joules. You got that right? Well done. Another key idea now. This key idea is work is done when energy is moved. And the total amount of work you do is identical to the amount of energy that is moved. So we've got a little problem here, for example, Susie putting a box on the shelf, storing 1000 joules of energy. How much work is done putting the box on the shelf? Well, that is pretty easy because the work done is the energy stored. If she stored 1000 joules worth of energy, then she has done 1000 joules worth of work. Really is that easy. Whatever the amount of energy that is stored, whatever that value is the same as the amount of work that is done. Okay, we're nearly there on this lesson. Little mini test for you to do then. Pause the video, have a go at it, and I'll go over the answers in a moment. Let's see what you should have done then. So the first one should have been 40 times 9.8, that's the mass, times the gravitational field strength, 392 newtons. The problem number 2, similar thing, slightly different numbers, that would have come out as 56 newtons. How much work is done by a 500 newton force moving something at a distance of 25? Well, 500 times 25, 12,500 joules. Make sure you've got the unit correct there. And how much work is done storing 1500 joules of gravitational potential energy when lifting a box? Well, that's just the same number, isn't it? Work done is energy stored, so that is 1500 joules. Again, on all of those, don't forget the units, they are important. You've got them right, well done. But that's it for today. Anything you didn't understand, feel free to rewind the video and have another look. Otherwise, that's all, folks. Thank you very much.